Hello there, this is the third episode of our ODE series. In this episode, we're going to discuss an exact differential equation and the integrating factor. When a differential equation is called exact, that means we don't need to use any special technique to solve the equation. On the other hand, when we encounter a non-exact differential equation, we need to find the integrating factor and multiply the differential equation by it. In so doing, the original non-exact differential equation will become an exact one. Therefore, we can reap the benefit of not having to use any special technique to solve the equation. Okay, so let's get started. Exact and exactness. A first-order ODE, m as a function of x and y plus n as a function of x and y times the first derivative of y equals 0. This one can be rewritten as this expression. And if this ODE is called exact, meaning that it has the form of this expression, which is the total differentiation of u function. But before we call this ODE exact, a condition has to be met in advance, and that is exactness condition. Let's jump to the conclusion and take a look. The exactness condition is partial m over partial y is equal to partial n over partial x. This is the condition which has to be met in advance for the exactness of the ODE. But with the hindsight, we know that this exactness condition is a necessary and sufficient one to the exactness of the ODE. A necessary and sufficient condition means that if statement 1 is true, then the statement 2 is also true. Likewise, if statement 2 is true, then statement 1 is also true. So statement 1 and 2 are necessary and sufficient to each other. Unfortunately, we cannot prove the exactness condition being necessary and sufficient to the exactness of the ODE for now, until we go to chapter 10, which is about path dependence of line integral. So we will take this exactness condition being necessary and sufficient to the exactness of ODE as a prior knowledge. Now we want to deduce this expression for the exactness condition. First, we want to know what are statement 1 and statement 2 in this case. Statement 1 is about the exactness condition, and statement 2 is about the exactness for the ODE, meaning that the ODE has the form of this total differentiation of u function. So we decide to go through the reasoning process from statement 2 to statement 1. So please remember, statement 1 is our goal of reasoning. So let's start from statement 2. Statement 2 tells us that the ODE has the form of this total differentiation. So by comparison and inspection, we can see that m function is equal to partial u over partial x, and n function is equal to partial u over partial y. That is statement 2. So Based on statement 2 and by observation, we can see that partial m over partial y is equal to the second derivative of u over partial y and partial x. And then by the assumption of continuity, the sequence of partial y and partial x is irrelevant for the second derivative of u. So this one is equal to this one. And again, by observation, this one is equal to partial n over partial x. So we get the conclusion that partial m over partial y is equal to partial n and partial x. So this expression of exactness condition will be useful in our next slide. From this slide to the next, I want to introduce to you a diagram which embodies a visual reasoning process for an ODE to be exact. This diagram consists of a green route shown in this slide and an orange route in the next slide. So the green route starts from a total differentiation of an implicit function u of x and y to an ODE as the endpoint. The green route has been through total differentiation and a condition where u of x and y equals constant and an operation of being divided by dx. So the idea is to go backwards through this route from first order ODE to the implicit function u of x and y, which will lead to a very powerful solution method. We will illustrate that in the next slide. The orange route starts from a first order ODE to its solution as an implicit function. So the orange route embodies the visual reasoning of solving the ODE. So this ODE, after being multiplied by dx, become this expression. And when we take a look at this expression and the total differentiation of u beside it, it will remind us of our previous discussion on the exactness of the ODE. If the ODE is exact, meaning that we don't need to use any special technique to solve the equation. So in order to reap the benefits of an exact ODE, first we have to make sure that the exactness condition is met. So let's say if the exactness condition is met, then we can call the ODE exact, meaning that it has the form of the total differentiation of u function. So that brings us to the third step. Now we are entitled to designate du to this ODE, right? Because du is equal to the total differentiation of u. And because from the beginning the ODE is equal to 0, so du is equal to 0, u is equal to constant. Now we want to solve u by inspection, because m is equal to partial u over partial x, n is equal to partial u over partial y. So by taking integral of m with respect to x, we can solve u. Of course, don't forget the function k of y as the integration constant. And if you choose to integrate n with respect to y, don't forget the L of x as the integration constant. So up to this point, we have completed our visual reasoning process. I would like to restate that the orange route was inspired by and the reverse version of the green route. I think it's a very classic way of thinking and also very intellectually stimulating. I encourage students to engage themselves in such way of thinking from the textbook, even though it might not be very helpful for them in scoring high on their test. But this example is very reminiscent of the original thinker who came up with this idea and this powerful solution method maybe 200 to 300 years ago. Now we're given an ODE and we want to know whether it is exact or not. So we check the exactness condition and we find that this condition is not met through the calculation shown here. At this point, we can conclude that this ODE is non-exact and we cannot find a solution without the use of any special technique. But if you don't recognize the validity of the exactness condition and insist on further calculating, eventually you will find yourself being unable to find any solution. I wish not to explain all the detailed calculation here, so if you are interested, you can pause the video and take a look at this calculation process. So what we should do when we encounter a non-exact ODE? When we encounter a non-exact ODE, we should find an integrating factor and multiply the ODE by this integrating factor. So the non-exact ODE will become an exact one. Therefore, we can reap the benefits of solving an exact ODE without the use of any special technique. So in a subsequent slide, I designed a diagram reasoning the process of finding an integrating factor. So let's go and take a look. Let's say we have a non-exact ODE pdx plus qdy equals 0. And we assume an integrating factor f, and we multiply the ODE, the non-exact ODE, by f. So the original non-exact ODE becomes this one. fp dx plus fq dy equals 0 should be an exact one. Because this is assumed to be exact, so the exactness condition has to be met. We take the partial derivative of fp with respect to y, which is this one, and we take the partial derivative of fq with respect to x, which is this one, and they should be equal to each other. And then we assume that, actually it's not assumption, but generally speaking, f should be f of x and y. So this exactness condition expands into this expression, and the subscript y means we take the partial derivative of f with respect to y, and this subscript means that we take the partial derivative of f with respect to x, and we find that f of x and y makes this equation too complex to be solved. So what should we do? In a subsequent slide, we will assume f function as either f of x or f of y to simplify this ODE in order to find integrating factor more easily. So previously we expand the exactness condition into this expression, and we said when f function is a function of x and y, it will make this equation too complex to solve f. So we take the first assumption as f equals f of x. So it will simplify this equation into this one. And then we shuffle the terms to turn this expression become this one. And you can easily see that this expression is solvable if our function is a function of x. So we integrate both sides of this expression, and we get f of x equals the exponent of the integral of r of x with respect to x. And because the integrating factor f is solvable, so we prove that equation star is exact. This one is exact. So now we can reap the benefits of solving this equation by simply integrating. So this equation star, we can designate it to du, and it is equal to 0. And by simply integrating, we get u function equals the integral of fp with respect to x plus k of y, or if you choose to integrate f star q, take integral of if you decide to integrate f star q with respect to y, you will get this solution. And don't forget the function L of x, which is integration constant. So previously, by setting f function as a function of x, we simplify the partial derivative equation into a simpler one. And if r of x function exists, f will be solvable, proving that this equation star is exact. So we can get the solution u function by simply integrating. So likewise, we can choose the integrating factor f star as a function of only y. So the subsequent reasoning process is pretty much the same. So you can pause the video and take a look at this green route. To sum up, you can either choose f as a function of x, whereas an r of x exists, or you can choose f star function as a function of y, whereas an r star of y exists, and then you can get f and eventually solve the equation. Finally, we have come to our takeaway points. I tried to integrate all the things we have discussed previously into a few and concise expression. So when we are given a first order exact ODE, this one, so this one is equal to this one, which is the total derivation of u function under the premise of the exactness condition, this one. So if this expression holds, then we want to solve u. So by integrating m with respect to x, we can get u. But don't forget the k of y as an integration constant. But because the k of y is still unknown, so we take the partial derivative of this one with respect to y, and this one should be equal to n, right? This one should be this one. So by this expression, we can solve k of y and eventually solve u. Now we are given a first order non-exact ODE, this one. Because this is non-exact, so we cannot solve this equation by simply integrating. We have to find an integrating factor first. Because this is non-exact, so the exactness condition will not be met. So we multiply the equation by f. So the equation becomes this one. And because this equation should be exact, so the exactness condition should be met here. And if we choose f as f of x or f star of y, whereas r of x or r star of y exists respectively, then supposedly we can solve f from this expression. This is the result of shuffling terms from this expression. So if we manage to solve f, then we can prove that this one is exact, and therefore we can designate the total derivation of u to the this equation. So we can solve u by simply integrating, just as what we did in the previous slide. In this episode, we have managed to visualize the following. First, we visualize the reasoning process of the exactness of an ODE, and we also successfully visualize the process of finding an integrating factor for a non-exact ODE. And also we make a concise cheat sheet of finding a solution of an exact ODE, and also finding an integrating factor and thus solution of a non-exact ODE. So this is how I deal with the calculation details some visualization into a colorful diagram or simplification into a few concise expressions. I hope you like my idea and creation in this episode, and I hope you enjoy it. So see you next time.